All right, so basic idea, again, just a quick review of segmentation is that once my, there we go, slideshow shows up. So basic idea is that we want to look at the image and identify different phases in the image, which in X-ray tomography at least, they're identified by the different density. In different other imaging techniques and might have different differentiation between phases. And I want to basically simplify my world and just divide it into different bins or phases. So here I would like to separate air, water, and glass beads. And looks like it's a reasonably easy thing to do in this image. If I actually pile together a histogram, I should be able to kind of draw a line between different phases and see them separated. Well, this simple thresholding is the basic and very cheap segmentation method. However, that basically defines a threshold, and everything below the threshold is one phase, everything above is the other. I could do it multiple times, so I could have multiple thresholds, of course. But in cases where I have merged peaks in my histogram, they're not good candidates for simple thresholding, and you're going to create quite a bit of error. So basically here I have so much noise that, yes, I see the individual phases, but obviously the surface area is too rugged and I have way too much noise. Now, I could still average, in terms of if I was just computing porosity, I could actually find a reasonable value from this segmentation. So depending on the task, you might be doing just fine, but that's because I have plus my positive and negative errors, so to speak. So identification of grain that is solid, that is pore, and identification of pore that is grain kind of cancel each other, essentially, if I have noise like this. So my porosity average, which averages the number of those, will actually calculate correctly. Okay? But that doesn't mean that I have quality image that I can work with, especially if I want to do simulation. Okay? So just evaluating porosity and finding a satisfactory number means nothing in terms of evaluating your segmentation. Okay? Now you also have to be careful depending on the image you have. Let's say that you're dealing with microscopy. This is actually a beautifully clear image of a capillary with oil and water. Well, because of the reflection in microscopy, I'm going to have issues in identifying actual phases, because all we work with in images is the grayscale values. So here, for instance, this is going to, and I might even, when I look at the histogram, I could say, okay, I see, 2 or 3 phases in there, but separating means nothing here, because I'm going to pick up these reflection parts as too dark or too light, and they can actually be very physically wrong. Even if I find to fix this one up, where I basically just remove this inner portion and call all of this oil, it seems that I have a layer of wetting and non-wetting fluid along the solid surface, which is physically wrong here. Okay, so this appears as a layer of non-wetting fluid simply because I have a dark line. Okay, and therefore I have to be hello. No. Somebody else has an issue. Not me though. I don't think I pressed any buttons, did I? I don't think so. Typically there's that little interval. Oh, that, yeah, I didn't press that. Okay. So essentially here, this, for instance, this layer could be interpreted as some sort of non-wetting film, which is not physical here. So you have to be careful that your grayscale value is not misidentified, because all that we work with when we're doing segmentation is grayscale values and maybe their derivatives. Okay? So look at your image. Now there's multiple, I went through the number of algorithms last time around. I'm not going to repeat that. We're just going to, and in software, there's a number of software. This is the one that I haven't tested yet, but it does look promising because it's C++, so should be reasonably fast, and it implements threshold and watershed segmentations. And in commercial, MATLAB is good for smaller scales images, and it's good for learning. It has very good online webinars and stuff like that. So it's definitely a resource that it's worth considering. However, if you're doing with 3D images, you will soon find MATLAB really limited. And then there's Aviso, which is now per geos for a large scale. This is going to be exemplified in lecture on surfaces. This is a commercial version. It also has basically threshold and watershed segmentations implemented. Now, you might have noticed already in some of these images that it's going to be necessary. Let's say that my segmentation, whichever algorithm I decided to do, results in something like this. Okay, I can obviously see that like these are misidentifications because of the noise. Okay, so I have these small objects that I might want to remove. And I can simply go by size and say, well, pick these small isolated regions and remove them and sort of convert them to the opposite phase. Okay? Because in this case, unless I know that I have some particulate hanging in there in the middle of the pore space, okay, maybe suspended in a fluid, they're non-physical. Okay? Now, sometimes they might be disconnected for finite resolution reasons. I might have like a thin neck that I didn't properly identify, so then it appears that this portion of my hand is disconnected because I didn't identify this as solid, right? Now in that case, I have also error like this is actually solid, this portion of it, but it appears that it's also hanging in the air, which is non-physical, right? So I might have these disconnected objects for various reasons. Now, it can be finite resolution issues, it could be simply noise, but I misidentified one phase as the other. So in any event, more likely than not, you will have to basically remove some of the objects that you have because of the misidentification, or because you don't want them to cause trouble in whatever you are doing later. If you're doing simulation, such disconnected objects can create issues. And if they're representing less than 0.01% of your phase, it's not going to really affect your solutions in a major way. So first thing first, you identify how many and how much of them are there, and then you decide which ones to remove. Okay? And you can, in ImageJ, just in 2D images, you can do despeckle for some small stuff. But actually, this median filter on binary images works rather well for that purpose as well. So it's going to remove a lot of some small speckled noise. One thing that is dangerous is to kind of erode and dilate your phases, which is something that we're going to talk about in our next lecture. It has to be used with caution because it can actually modify large portions of your image. So this is going to be a separate topic, but I just wanted to give you a heads up that typically after segmentation, you will have to do some essentially filtering of your segmented image as well. So you likely did some filtering with the grayscale image in order to do a better job with segmentation, and then after that, you might need to do it again. All right, so we start with tomographic image. Then I have to choose an algorithm to identify what is my pore space and grain space. In this particular case, you might have a different problem, but the simplest is this binary segmentation. And I have to choose a segmentation algorithm well. This particular one, because of the noise, I either need to filter this really well to get a better quality solution, or I need to apply a method that can deal with this noise statistically, okay, and is robust with respect to noise. And in this case, this would indicate a kriging, but for instance, watershed segmentation will do rather well as well. And we will mention some others. So we want to, watershed is actually, we're going to kind of deal with that a little later because it's also one way to identify individual grains. Let's say that I have a granular image of a granular material, or it's a way to identify individual pores in my pore space. So in that lecture, we're going to deal with segmentation, watersheds for segmentation. Now, we want to, basically for each voxel and pixel, we want to figure out which phase it belongs to. And you do have to find a way to evaluate it to yourself whether the segmentation you do is the quality. Now, you possibly want to compare to whatever you get in experimental measurements. Word of caution is that all experimental measurements are on slightly different scale. That doesn't mean that you shouldn't do it, but a perfect match is not necessarily possible because it's not comparing apples to apples. It's comparing very small apples and very large apples. Okay? Small apples. Play a role in transport. So I could have some interface transport, mass transport, and so forth. Or I might simply want to quantify surface because, for instance, absorption is important. This is very appealing for surface measurement. And again, you might want to compare with available method. The available method is BET. That's the common method we do in the lab. But you have to realize that in the lab you're going to crush the sample some, and when you're going to basically let gas absorb. And this method assumes gas either building in one layer or multiple layers, but even layers that are distributed everywhere. And then based on that assumption, it will compute, and based on the amount of gas that went into the sample, it's going to figure out how much surface I have. Okay? So there is some underlying model that is assumed. So I might get numbers that are very different from whatever it is that I might measure from images, because with images, I'm stuck on a particular length scale. And if there is surface roughness that is below my resolution, I will not see it. Okay? So I almost have some sort of fractal behavior of a surface, whereas in BET method, it's the gas molecules that go in there and figure out where the surfaces are and how to attach. So I have sort of like a different level of resolution. So comparison, you should be very careful with the comparison. Okay? And this is one of the papers. There's actually a story to it. I actually started working on this early when there was basically not that much stuff. This is my second year of my grad school, okay? And I actually figured out, I can find out surfaces. I implemented the algorithm, and I got some results, I tested it, and I'm like, yay, I can publish a paper. And then these guys literally published it like a few months ahead of me. Oh, well, too bad. Moving on. Now it's a good day. A surface in porous medium. It's not a big deal nowadays to find that surface, and any visualizing software will do it for you. We'll do more on surfaces in later lessons. Let's do an exercise. So I have shared a segmentation exercise folder with you. Go to it. Yes?
So when you do filtering, do you think it's more important to spend more time, before segmentation, or is it better to do do it post-processing? Or does that always depend on?
It depends on, I would remove as much noise from an image by filtering that I can. At the very minimum medium filter. You're not going to do a lot of damage, but you will actually improve the quality quite a bit. And this is where you have to tread lightly, because definitely good filtering will make it easier for you to use a method, use any method for segmentation. So question is also, what tools do you have at your disposal? I'd say that filtering tools are more widely available and implemented than segmentation tools are. So quality segmentation methods could be actually much more time consuming than filtering is. So I'd filter rather well and then move on to segmentation. And we're going to actually have an example that carbonate samples that you're playing with right now, they actually have some interesting features, and basically you have to denoise them in order to actually use segmentation properly. So yes, I'd say filtering, it's time well spent investigating filters. All right, so import beats data, and this is 16-bit data, and it's also 16-bit unsigned. And it is a big endian, so don't click little endian here. Otherwise, a lot of fun is to be had. And it's 695 by 695 by 200. So it's just a little portion. So again, it's a volumetric stack, so you have to go through import rather than open. Don't open volumetric images. Unless it's a volumetric TIFF image, then you can. Import raw. Oh no, this is big. No. So always also watch the memory. Not very big, but the size here could surprise you. Oops. I did something wrong. This is an exercise in how to import garbage. Friday is a garbage day in my neighborhood. All right. Kind. Okay. Oh, this was the problem. And you know why? Image J is trying to be smart. 16, 695. So first number is interpreted as a dimension. And this is actually something that has recently changed. I never had this problem with this, and I've been opening this file regularly since 2011. So it's trying to automate things, and I wasn't paying attention because obviously I need this cup of coffee. That. So implication for storing file names, do use file names that have all the possible information you need. What I'm actually missing here is the unsigned part, okay? But it's obviously, given this new functionality of Fiji, you might want to do dimensions first and then 16.16-bit later after that. So it's not going to automatically try to be smarty pants. Here we go. This is microtomography. Somewhere on the order of 5 to 10 microns, I'm not now entirely certain. You can see that I do have some imaging issues, possibly things moving here. And my beads are not completely perfect. Not on micron scale anyway. So no matter what, I will have a little bit of dots here, which might cause issues with my modeling and I might want to remove. Okay. But for now, did everybody import it? All right, let's go through the exercise. So first things first, actually kind of move around. See, so this is 16-bit image. As I'm moving, you can see the values. So you can see 16,000. You can see this 40-something thousand and so forth. This is a holder, okay? This is glass. This is air, okay? We can do histogram of the entire thing, but that histogram would also histogram the holder and the air, so I'm going to skip that for now. Let's first select oval and ignore anything outside of this holder. So you can play with fitting this. Now, nobody reminded me, but what did I forget to start? Record macro is always a good idea. So I'm going to do that. Record. And I'm just going to let it play here. And you will see, whoops. And I'm going to repeat my... So you can see how this make oval is a command. And once I fit something well, I might need to use that information on the radius of this cylinder. It might be important for my modeling. Okay.
Is it better to make it a perfect circle by doing shift and then clicking?
That's up to you. It's going to be hard to perfectly fit. That's one learning. Some automated selection of a circle might not be a bad idea. So this is now 542, 542, so that's a circle. If I'm off by 1 or 2, you might not be able to see, depending on how good your glasses are. Mine are never good. So you might want to monitor here that you actually hit the circle, if that's important. And then remember that it's a manufactured cylinder. So question is, even if somebody manufactured it, what was their precision, right? This is one way to test it. Okay. Next thing you will actually notice, whatever fits in the frame, so this is, whatever fits in this frame is not necessarily what always fits the same in other frames. Ever so slight shift. Well, there might be ever so slight shift. We're talking about microns here. Okay? And especially with the medical CT downstairs, you have a much larger object in the CT, so you might be slanted. Okay? So you will see that this circle kind of fits ever so slightly different in different slides. So you might want to go a little inward if you want to. That's now I'm going to leave up to you. For this particular exercise, it's not important, but it might be important for whatever you want to do with it. Okay? Okay, so now we're going to do that standard edit clear outside, so we can actually ignore the outside and do the histogram of inside stuff. Edit clear outside. And you want to process all of 200 images because that's a stack. Yes. Boom. All right. Now I want to histogram because now I know that I'm histogramming only inside stuff. And I see two well-separated peaks. And that is typically good for segmentation. So this is where thresholding is justified as an okay method, and that's what we're going to try. So you can analyze this histogram. You can output it in whatever you'd like. And depending what your settings are, hello. So these are the graduate students in our department. This is a visit. Would you like to introduce yourself? So we're playing with image of glass beads. You might want to sit with somebody. So right in front of you is Rui. Rui, are you following along or? Do you have computer open and are you working on anything? Yeah. I don't see. You're in the back. So so that you can work along. So basically we're trying to identify glass and air here in this image. And when I histogram all of this, so these are the grayscale values if I'm moving around the image. As I histogram it, I will see this peak. So this is the peak over higher values. So those are my glass beads. They're light gray. And this is my air. So those are the two major populations. So segmentation should work. So let's use image adjust threshold. And why don't all of you pick slightly different values? So anywhere here, okay, is sort of a fair deal. If you move your threshold ever so slightly from here to here, the difference between those two choices is whatever the volume fraction is of this many images, okay, of this many pixels. So that's not a lot. Let's actually see how many. So this is difference between choosing a threshold at 30975 and 31 and next one up. Let's do bins list. So here, if I move from this bin to this bin, the difference in number of pixels that are in that category, or voxels, is about 30,000. Okay? 30,000 divided by 700 or 695 times 695 times 200 is not a lot. How much is it? What is it volumetrically? Where's my MATLAB? Can somebody compute, or should I ask Google? I thought I had MATLAB open. Let's ask. So it's 30,000 divided by 695. By the time I type this in, MATLAB will open. Okay. So this is so it's 0.03% of my entire image. Not a big deal. Even if I look at it as a fraction of the pore space, I'm still in 0.3% of my entire image. Not a big deal. Okay. So or my entire pore space. So it's not a huge mistake that you're making by moving threshold a little to the left or to the right in this particular range, okay? Because the counts are low. So let's do it. Let's threshold. Image, adjust threshold. Okay. This is a default image. You can also go by any of the method. Also is one of the more, okay. You don't need to calculate threshold for each image because it's gonna do different things on different level. Apply the single threshold. And this is my image. What do you see? Have here half moon of sorts. Okay. So this is how much I went into the cylinder. Okay. So you can see little mistakes like that when you do the, and there's less of it as I go up because image is essentially slightly slanted. Okay. If you're bothered by that, you can start all over. Okay. So I can import again. Okay, and I will again fit. This is where it's actually good to have this running so that you know what you did before and you can quickly execute it. So I could have actually just created a macro that instantly makes this oval slightly smaller, right? So let's do that actually. This is how you would do it. Run raw. And then I'm gonna just say make oval to this, just smaller. I will go on 38, 38. I'm actually going to delete everything, create a macro. Not sure why it minimized, but here we go. I'll actually see whether it just now executes. Don't save. I'm just gonna run it. Yeah? Automation is key. Especially once you find the perfect threshold and your Fiji crashes and you have to do it all over again. Run the macro and save it often. Okay? So now I went a little inward. Okay? Now I forgot to record everything else, so I'm going to now I actually deleted it here. And this is how you would run the script. Okay, and there is a name of it and it's saved somewhere. Yeah? So I'm gonna now clear outside. Again, I should have remembered clear outside. Ah, it's still not good. Okay. Automation is, and I'm gonna actually set background color to white, by the way. And this is also why it never asked me to set the background. It's probably a default in that entire edit. And I'm gonna set it to white for a reason. More visitors, hello and welcome. Boom. Think it's better. And now I want to do the image adjust histogram. Oh, sorry, just threshold. I didn't, it's analyze histogram. I don't need a histogram. I saw the histogram before. This looks good to me. So if you calculate threshold for each image, it's going to go through the stack, and for every level, it's going to calculate what this threshold should be. But then you don't know which threshold is applied on which level. So don't do that unless you specifically want to be tailored to each. For some reason, you actually know that your gray values are skewed. But I would rather go and normalize your values, your gray values, as part of the filtering than apply a different threshold on different level. Especially, we're talking over, what is this, 200 slices. Each is about 10 microns, okay? Shouldn't be that much variation in threshold levels. So the same grayscale value should be similar everywhere. Okay. And you can also pick whether you want a black background and so forth. Okay. All right. All right. Question for the class. What is porosity in this image? Porosity is the fraction of black voxels in this image. Black is 255. This is 0. Because that's the first number I ever want from image analysis and forest media. What is porosity? If you didn't calculate that, don't go anywhere else. I want the number. What tool is helpful? I have a histogram. See how many black or white, depending what you did with the background.
30%.
30%? That sounds about right. What did you do to calculate though?
Just check the waste and the bean and then
So zeros in your case are, can you see? Are black. So based on that number, did the outside get counted or not as black voxels? This is where knowing what porosity, this is knowing your petrophysics class can be helpful. Sphere packs have which porosity generally? 30 to 40. Okay. These are actually equal size beads. If they're well packed, they're about 36% to 40%. If they vary in sizes, then there could be variations, but sphere packs are roughly in that order. So if you get something awfully different from 30 to 40%, okay, you did something wrong. For instance, if we didn't clear outside and ignore the outside, then in my case, black voxels would be black voxels, but in order to divide, what do I divide them by to get the porosity? The total number of voxels. So then it doesn't matter whether I'm counting the outside or not. Right? Another thing is to go to my make oval. I know what the radius of that cylinder is. I know how to calculate volume of the cylinder. Okay. So there are various ways you can do this. But the one basic problem is that you have a whole lot of other stuff around this image that you have to figure out how to discount if it's not already removed. Now, if you did some opposite thing and your background is still black, then in this case, it would be possibly, if you did clear outside, counted with the pore space, and that's dangerous too. So you have to do some common checks and some sort of lab measurement, even though it's hitting precisely the same porosity that you measured in the lab is not useful in evaluating segmentation necessarily. That doesn't really tell you whether you did a great job in segmenting it or not. But it's useful in figuring out, okay, did you make some gross mistake? You should get the numbers that are reasonable to expect. All right. So basic calculation would be to calculate porosity, and that requires counting. Now, in this case, I have to live with errors that I have. Well, they might be real. So, for instance, I can see that these beads have speckles. And actually, when I look at the original image, it looks like I have little holes in there. So whatever I was shopping for was not the most precise bead ever. And that's actually common. Natural rocks will be even more imperfect. So nothing to write home about. But you do have to work with that. And if you want to, for instance, look at that. You might also, around slice 47, you might want to go and investigate what is that in the image that caused the trouble. Okay, so images are rarely perfect. And we might want to decide to filter some. So this is thresholding result and converting to binary data. Now let's visualize it a little. You can actually do or the same orthogonal views that we did before. So this is my visualization of my stack from the side, and you can of course move that. And as you move, you can see this yellow line move across the stack. So this is not three-dimensional visualization. That's where I would create that surface, and we're going to get to creation of the surface too. For right now, we're going to just evaluate stacks as we have them. Okay, so orthogonal views are helpful. Now again, this decision whether this background is white or not, I think it's somewhere in this image, and I keep forgetting where, but there's selection options. Yes. Colors. There we go. Background, foreground. So this if you make this choice, then whatever you do in that, especially clear outside part, and like all of those functions will have these choices. Actually, that's gonna. So if I do, is it now actually gonna change my color to magenta? No, still yellow. Oh well. So Congratulations, you did the first proper segmentation of a volumetric image. And we have already gone through some basic quantification questions. Second question is a more difficult one. What is the connectivity? Are my pores connected? Now in this case, I can simply do a visual inspection through the stack, and it seems like I should be able to move through pore spaces and reach from one end to the other. Okay? In fairly open pore space, that's an easy question to answer. In something much tighter, which most real rocks are, that's not so easy to answer, and I actually have to have an algorithm search through for a path from one end to the end. Again, if I'm not connected, then my permeability calculation is that much simpler. It's 0, or it's below the resolution of the image, whatever it is. Okay? So those are the basic questions that we want to answer. And for the purpose of answering of porosity and connectivity, whatever little bead imperfections I had in those segmentations, I'm going to declare them as good enough. Okay? And I'm not going to bother removing them. But there might be an application where I would want to remove those. Okay? So that's where I'm saying that everything is relative to what you want to do with it. Okay? And we calculated porosity. All right. We're going to move on to different types of segmentation next time. I see you on Monday.